So this is the first assignment that we need to do, and in this assignment I am going to teach you a way of writing assembly code and also segmentation. So let us now start with a programming assignment where I am going to multiply two 10 cross 10 matrices where each element is a byte. So I am going to multiply two 10 cross 10 matrices where each element is a byte. I am actually that both the matrices that I am multiplying are the same matrix, so I am calculating a squared, then I will calculate a cube. So I will take a matrix 10 cross 10 matrix which is having which each element being a byte. So I have 100 bytes. I multiply that matrix with itself, so I get a squared. Again I multiply a squared with a to get a cube. And this multiplication is not the normal multiplication. So how do you multiply two 10 cross 10 matrix? So for I equal to 0, I less than 10, I plus plus. For j equal to 0, j less than 10, j plus plus. I am writing a simple C code. Cij equal to 0. For k equal to 0, k less than 10, k plus plus. Cij equal to Cij plus Aik into Bkj. Okay. So let me just put some labels here. Here your k will finish, then your j will finish, and then your I will finish. Your I will start here, your j will start here, the j loop I mean, and your k loop starts here. So to simplify our complete code, in this case what I am going to do is I am going to do a OR and then AND. So I am going to do binary operations here. So instead of plus I am just going to do a bitwise OR of the bits. Note that Cij, Aik and Bkj, all these are all bits, byte, they are all 8 bits. So I am going to do a bitwise OR of Cij with the output of the bitwise AND of Aik and Bkj. So this is the code that I want to execute. Now your A matrix will be stored in one segment, B matrix will be stored in another segment, your C matrix will be stored in other segment, right? And then we will also use function calls basically to demonstrate how the stack works and how a calling routine communicates with the call routine. As I told you in one of the earlier sessions that this had been one of the major vulnerability. So let us understand through assembly programming how passing of parameters actually work. So we will write a code where we write an assembly code through which we actually pass parameters so that we have a real hands-on experience here. So this is the problem that I would for which I am going to, this is the code for which I am going to write the assembly code here, and we will now go through the assembly code in detail. So as we had seen in the directory, the procedure is we will define 3 segments P, Q and R. Initially P will be storing A. Now we will multiply the A stored in P with the same thing to get A squared, which will be stored in Q. So I will in the segment Q, A squared will be stored. Again we will take the A squared in Q and the A in P, compute A cube and store it in R. to just make things a little bit, so to learn or to understand what we have learnt in the theory class, we will make this P as a read-only segment, while Q and R as the read-write data segments. And this max multiplication, the matrix multiplication, that every time I do this matrix multiplication, I call a subroutine which will take two segments as input, and one will be the source segment, another will be the two source segments as input, and it will give me a destination, it will fill the values in a destination segment. So this is how I will basically do a function call here. So what normally when I want to multiply these two matrices suppose I define a function for this, I will take the A and the B matrix as inputs, meaning I will take the address of the starting of the A and B matrix as inputs here. And I will also take the address of the starting of the C matrix as input. I will do these operations and store the value of C there in the address that is provided, right. So that means what I mean by address of A and B matrix, basically I am taking the segments, the details of the segments where A and B are stored, and then and also where I should store C, and I will store it back. So this is how, if I want to implement this entire matrix multiplication as a function call, and I call it from a main routine, so the way the parameters are typically passed would be through these addresses, and this is what we will be implementing here. And the notion of using call, as I repeat, will be to basically explain how the stack works, because we have already looked at stack smashing, where we explained how the stack works. We will see how it is doing with a practical demo here. So as we have seen there, we need the gdb comma, which is there in the directory. We need input.gdb, which are the commands, the test.ld, which are the loading options, and today we have lab1.s. This is typically what we will be using for the other assignment. It will be lab2.s, lab3.s, lab4.s, and so on. Okay. Right. So the execution procedure, we have already seen this. So you can go through this slide again if you had doubt. I have already explained that in great detail. Right. With this, let us again go back to the. Okay. Now we have loaded the entire code here. So let us start. So if you open lab1.s, what you see on the right hand side is the thing that you will see. Okay, so this is the code. Note that there was a dot text in the prod.ld file. I am going to the next here. So more prod test.ld. So there was a dot text, and we said load the dot text in 0x8000. So that's what you see here. So the dot text in this file, as you see on your right hand side here, the dot text will get loaded at 8000. Right. Now what are we doing here? So there is a GDB already running. So that will have its own GDT and IDT. Note that we are currently in privilege level 0. We go and store those values of GDT and IDT in code base plus 3FFA. What is code base? 8000. 8000 plus 3FFA is DFFA. So in DFFA we will store the old values of GDT, and DFF2 we will store the old values of IDT. So what will GDT contain? It will contain a 16-bit limit and a 32-bit starting address of the GDT. So we will just start making a note here. So I start from here again. In 0x DFFA, you are in line number 8 here, 0x DFFA, we will be storing old value, old GDB's GDT start address plus limit. Similarly, in 0x DFF2 will be storing GDB's IDT start address plus limit. Note that these two commands can be executed. What is the difficulty in executing these commands? Note that SGDT and SIDT are privileged instruction and they can be executed only by privilege 0 code. But when I am starting executing of this code, this is in privilege 0. So this will execute these two commands for sure. Then we clear the task switch. Then these are all some things basically to tell that this code is executing. So A1000 plus 3200 is D1200. I store the value def. So 0x D1200 I store the value def. And in D1208 I store the value 0001. And in the location DFF8 I store the value 0. This is line number 70. So these are all 8-bit movement, 4-byte movement. This is word. Word is basically 16-bit, that is 2-byte movement. So you may get as 0, 0, 0, 0. Right. After that, I load the GDT of mine, the GDT of this code. So the lab1.s, to basically explain you what is lab1.s, that code, basically all the codes that we'll have as a part of this assignment, this is the memory map of our code. 0x A1000 to 0x AFFF, we'll have the code of the program. 0x B1000 to 0x CFFF, we will have the data segment, data of the program. And 0x D000 to 0x DFFF will be the operating system area. So when we load the program, we have a small mini kernel also loaded. So note that in now this memory map we will follow. Note that all that we are doing here so far, like storing the old GDT, IDT, D20, all these things are in this page D1000 to DFF, which is the operating system area. Now what next step is, the operating system actually stores my address at the GDT address, my GDT. So for executing my code, because I will have my own segment, I need my own GDT. So the 0x D202 will store 0x D202 will store the GDT address. Address plus limit. Okay. Now let us go and find out. So go back to this window here on your left hand side. Let's just say x slash, now that is 16 by, so 4 plus 2, 6 bytes. So x slash 2x 0x d2 02. Now we will know that the limit is ff, or actually 00 ff. The base is d1000 and plus 00. So there is a 16-bit limit which is ff and 00 ff, and there is a 32-bit start address which is 0000 d000. Okay. So from this we will get that. So I am making another statement here. I'll say my OS page. So GDT starts at 0x d1000 and this of limit 0x ff. Similarly, let us go back to the next statement here. Your IDT slide number line number 22. The IDT base and address are stored at D20A. So your 0xD20A will have IDT address plus limit. So let us go and say, so the IDT starts at where? So for that we go and say s slash 0x D20A. Your IDT starts at D210 and it has a limit of A0. So it has a limit of 00 A0 as I am marking here, and a start address of 0000 D210. So your IDT starts at 0x D210 and is of limit 0x00 A0. Now just as a sanity check, let us go and find out what should be so each GDD is 8 bytes. So I'll just put s slash 2x 0x D000. It should be a null descriptor. As you see that the first descriptor in your GDT, which is stored at D1000 to D1000 1, 2, 3, so 4 bytes, 8 bytes. So 0, 1, 2, 3, 4, 5, 6, 7 is first a null descriptor. Now we want to move AX, 0x58. So the AX register gets 0x58. Now I am loading LLDT with AX. So what is LLDT? It is local descriptor table address. So what is 0x58? It is a selector in the GDT. So now how will I find out what is the value? I say x slash 2x 0x D058. And note that this is pointing to this is basically a TSS selector which starts at D100, and this 82 basically tells that this is a TSS selector of privilege level 0, right? So basically this is a LDT selector of privilege level 0. 0x58 is an LDT selector, and the LDT starts at D100 and is of size 00. FF. So this is what I set up the LDT in case I need it. So let me go here. So the So the 0x58 in GDT stores a selector for LDT. LDT starts at 0xD100 and is of limit 00. Okay. Now we see what is 0x60, x/2x, 0x D060. What is that? Please note that this is basically a task state segment descriptor of privilege level 0, 4089 here, and is a 32-bit task state segment descriptor which starts at DA00 and its size is 67. As you know that the task state segment has total bytes which is 6 into 16, 96 plus 7, 103, total 104 bytes. Right. So this basically is a task state segment descriptor which starts at DA00 and of size 67. So I should also note here that 0x60 in GDT stores a descriptor to current task, for current PL0 task. It shows a TSS descriptor. TSS for PL0 task starts at 0xDA00 and is of size 104 bytes. Size 104 bytes. Okay. So this is what it is currently executing. Okay. Now we are moving 0x10 to DS, SS, ES, FS and GS. Okay. So what is 0x10? Let us go and say S/X, S/2x, 0x D 0 1 0. Please note that this is a segment starting at B1000 and has a huge limit BFFF. And it is privilege level 0 and it is a read writable segment. So we will go back to this now. Zero x10 in GDT is read write segment, read write data segment with start as 0xB000, limit as 0xBFF. Okay. Right. So at the end of this, all these selectors will now whatever you write will start from B1000 and whatever offset from that, and they are all PL0 segment. Now what is 8? Zero X D008. This is a code segment which starts at 8000 and it is of size limit FF. F followed by 4 Fs, as you see here. There are 4 Fs here. There is also a small f here. Okay. So this is a huge segment. So now you jump to this 0x8 with an offset start minus code base. This is start address and code base is on the top. This is code base. The code base starts at 8000. So what is start minus 8000? Is basically your start minus 8000 is total number of bytes consumed by the code above it. So when I say, so this will be from 8000, whatever be the number of bytes consumed will be this start minus code base. So if I say jump 0x8 colon start minus code base, it will take the base 8000 and it will add so many bytes which is given by start minus code base and it will jump. That means it is going to start, it will jump to move d word 0x1ff0 0x0. So it's basically coming to this. Why it is coming to this? Why do I need to do this jump? Because I need to switch from my GDB's code segment to my own code segment 0x8. Here I have switched on to my own data segments here. Now here I am switching on to my own code segment here. Now it makes move d word 1ff0 0, move ESP as 1ff0 and pop ft. So it is initializing all the flags to 0. Pop. So you now move to what is d word 1ff0 because the base is B, BFF0. So it is, we are now moving to 0x BFF0. We are moving the value 0. D word is double word which is 8 bytes. I am moving value. And I am making the stack pointer also point to 0x1ff0. I am doing a pop ft, essentially 0, it will go and initialize all the initializable flags. And now I give control to the code. Right? So what we have done so far is what the operating system normally does. So it creates memory, it loads the program, it sets up all the things, and now it gives control to the code. So we have described this entire process. So further it will execute this code and after that it comes to this stage where again it moves AX comma 10 DS comma AX. So what is GDT is D010, it's a segment starting at B1000 and of size BFFF. Then what it does is it goes and loads the stored. Please note that we have stored at DFFA the previous GDT and LDT IDT entries. It loads it back and it does a jump 0x8 colon fin. It comes here. For this GDT. Now the GDT has changed. So this 0x8 will now correspond to the GDT of the GDB and it will come back. So this is the way the operating system moves, the GDB kernel moves from itself after initializing initializing certain things, and you start executing your code, and after you finish your code, you actually give back control by getting their GDT and IDT loaded, okay, and we do this in 3. You set up all these things with the new GDT, and you do this in 3, which will take you back to the GDB prompt.